We are going to present our final year project, Printcare, which our supervisors are Dr. Subodha Charles and Dr. Ranga Rodrigo. The external supervisor of our project is Janith Gunaratna. 3D printing is a manufacturing process that creates three-dimensional objects by layer material based on 3D models. So there are several number of 3D printers in the market, several number of and several kind of type of 3D printers that summarize the main three types of 3D printers. First one is the FDM filament-based 3D printers, which extrude melted filament through the nozzle. Next one is the resin printer, which where the UV light is projected on the resin, which is hardened by the patterns created by using the projection system. Last one is the laser printer, where the metal powder is melted and composed in the structure, which is fed by the laser beam. Let's look at how the 3D printer process works in general. First, we have to create a 3D steel model from a 3D any 3D CAD software like SolidWorks, and then using a slicing software, we can the model can be divided into layers. Those layers can be translated into G codes, and the G codes are the instructions which is given give the nozzle to perform several motions, like go 3D 5 centimeters left, like half cycle, draw half cycle, or measure temperature of the nozzle. Those kind of tasks can be performed directly using these G codes. The G codes is the collection of G codes can be used for printing the whole object. Anyway, due to many more reasons, this process can be failed. One of these reasons is not having a proper parameter set. They can be changed during the middle of the process, or they can be material property change or unexpected environmental issues. Those kind of issues can be caused for any of these kind of 3D object fail, 3D printing fails. Our primary goal is to develop a real-time detection of these kind of issue and correction mechanism using computer vision techniques as well as machine learning techniques to enhance this process. Like as for example, we can convert this left side image, left side model, into a smooth, correctly printed model in the right side. So that's the primary goal. Let's look at the system architecture of our project. We have main application which receive the nozzle camera input, the G code file, and process that G code process the ML task to get the correction G codes using the camera feedbacks, and then we can give the corrected G code file to print the model using the 3D printer. There are two cameras in our architecture. One is called outside camera, and the other one is nozzle camera. Outside camera is used for certain machine learning tasks like object detection and localization, as well as object fault detection. Other errors like most frequent errors are detected, and real-time correction is done by nozzle camera. Let's move on to objective 1.
Objective 1. This is the first objective of our project. To take the manual control of the 3D printer, we created Python script that can send line by line G codes to the 3D printer. So in that case, we use UART protocol to communicate with the 3D printer. So let's move on to the objective 2. So error detection and correction using the nozzle camera. So first move on to the hardware setup. We created mounting part for the camera using SolidWorks, and that part mounted to the nozzle head, and you can see in the slide where the nozzle camera is placed on. An endoscope 1080p resolution camera is used as the muzzle camera. So let's move on to the error detection model. This is the architecture of the model we use. According to the model, there are 4 outputs: flow rate, lateral speed, Z offset, and hot end temperature. There are subcategories as well. Those are divided as low, good, and high. Using those errors, we can identify follow errors. So we can identify overextrusion using high flow rate and the low lateral speed, and underextrusion, low flow rate and the higher lateral speed. Object detaching from the bed, we can identify using the high Z offset, and hot end overheating, we can identify by the higher hot end temperature. Let's move on to the training part. So into training the model to general features, we use the Caxton dataset. So in that case, we use 1.2 million images over 192 prints. So follow the training results you can see in the slide. To train the model for our dataset, we use the transfer learning techniques. So here we used 50K images as our own data, and these are the training result we got from the transfer learning. So this slide explains some predictions we got from our model. So these predictions are given like format. First one is coming flow rate, second one lateral speed, and Z offset is the third one, and the hot temperature is the last one. So subclass we divided like low, good, high. Those are indicated using 0, 1, and 2 respectively. So let's move on to the third object.
The third object, we take outside camera feed and notify the user and the command the system accordingly. Here we use camera mounted on the bed to the, like it is called outside camera, to make sure the printed part is not moving related to the camera. So that we designed the camera mount as you see in this picture. As you see in this picture, designed camera mount and fit this camera mount to a specific location of the printer, as you see in this picture. For the algorithm part, we have chosen YOLO V8 because there are several reasons. The first reason is we wanted to get the real-time feedback from the YOLO machine learning algorithm, and the second one is difficulty of finding small objects from other algorithms. So YOLO V8 was suitable in both occasions. First, we collected the dataset from the internet and from the outside camera as well. And for that, for the outside camera dataset, we printed a lot of faulty prints, 3D prints, and got images of them. Then we used the RoboFlow framework to annotate the dataset, then trained the dataset for YOLO V8. As a result, we could achieve the labeling of errors with 0.367 of the MAP 50 on the overall validation set we have. Next, look at the objective 4. Next, look at the objective 4. Next slide, please. In objective 4, we are using outside camera to detect errors and using mathematical algorithms and image processing. The 3D world locations are calculated. Next slide, please. Here is how we calculated the intrinsic camera matrix of the outside camera. It is essential when we get the relationship between world coordinates system and the image pixel coordinates. As you see in this picture, by taking the image of the chessboard with certain dimensions, we can easily calculate this camera matrix in OpenCV. Next slide, please. Next is the relationship between the world coordinates and the image pixel coordinate system. As shown here, U and V in this X coordinates are the image pixel coordinates. So the point we can get as a image coordinate like 150, 480 likewise. So K is the intrinsic camera matrix, and XW, YW, ZW is the coordinate of real world, like 3D world coordinates. RT01 in this the matrix shown here, it is the resultant homogeneous transition matrix between the camera coordinate system and the bed center point coordinate system. It is calculated using HBG, that is relative homogeneous matrices between the bed and the bed center point and the ground center point. And camera and bed center point is homogeneous matrix is HCB. The the notations are given as you see here, and they are calculated with lot of precision. Next slide, please. Next is the test results we found. As you see here in this picture, 1500, 1050, 1056, 480 pixel is detected as erroneous. There can be several points in the 3D world coordinate system that can be that satisfies this image coordinate, as you see in this picture in the right side. All the corrected all the pixels mapping to this image coordinate is shown in this are calculated using our algorithm, so it is correctly calculatable. In the next slide, you can see this the next objective we have, objective 5. Here we are using outside camera to detect object fold errors. This is uncorrectable errors. Next slide, please. First, the printing object need to be color segmented correctly by using manual techniques, manual adjustments of the panes shown in this window. HSV model is used for color segmentation, and the result is at the moment printed objects camera projection, as you see in this last image. Next slide, please. The steps are simple for object fold detection. The mask is taken as the previously mentioned calculation, previously mentioned technique, like the manually adjusting the panes, and using the G-code file we can convert the 3D world coordinates into image pixel coordinates. By correctly coincide the two images, like the mask and the G-code converted into image domain, we can get the percentage of coincide, like 50%, 60% like this. If we find that there are the coincide percentages exceeding the limit we are proposing, we can say that it is not fallen. If the percentage is lower than the threshold, we can say it is fallen. There are some limitations in this method. This method is heavily depending on light condition of the environment, especially the bed light condition. The object need to be separately seen in this image as well. If they are printed very closely, we cannot find this fall detection as well. So they cannot be intersections between the objects. Next objective, we'll explain.
Here is a first example. It is a dual camera printer setup with each camera detecting errors in separate methods. You can see in the picture, one camera is mounted onto the nozzle, and there is a web camera monitoring from outside. So from this setup, we are able to identify errors, but we are not able to correct every error that is identified. But we are able to correct some of the errors like over-extrusion, under-extrusion, and overheating. But for the moment, stringing, spaghetti, and media printing errors like lace and nozzle clogging are not correctable. And other including each of these functionalities. You can see the UI of the application here. But first, we can select the serial port printer is connected and upload G-code file to the app. Then there is a button to start the print. And application controls the printing as usual from that moment. Then there are two buttons to start nozzle camera detection and outside camera detection. Then if correctable errors are detected, correction happens automatically. If uncorrectable errors are occurred, a notification sent to user's mobile phone before pausing the print. And also reconstruction is happening parallel for everything. And while doing the project, there were some challenges we faced. The main challenge was the nozzle camera. The images taken were not clear enough, and lighting was also affecting image quality. Then we tried by changing the camera angles, and control the lightings by creating a chamber to cover the printer. And in outside camera, also there was a lack of training data to be found from the internet. So we had to print quality print plans and create the errors. In 3D reconstruction also, at the beginning, it took too much computation work and failed to update in real time. Then we tried optimizing the code and tried with different Python packages as well. For the merging and creating app, some platforms didn't support some features we need. So we moved to different platforms. And a great job to success of project 3D Printcare. Thank you.